Could there be undiscovered intelligent beings in the vast expanse of the universe, hidden or preparing for significant actions? Perhaps advanced civilizations are deliberately concealing themselves, or they might be on the brink of monumental endeavors. Moreover, what if unraveling the mysteries of the universe hinges on encountering life forms composed of silicon? Recently, the space agency announced a breakthrough suggesting the potential presence of an oceanic world based on its analysis of atmospheric composition, bridging science fiction and reality. More than a century ago, H.G. Wells captivated audiences with imaginative works like The Time Machine and The War of the Worlds. French filmmaker Georges Méliès took this fascination a step further in 1902 with his immensely popular fantasy, A Trip to the Moon. Wells wasn't the first to propose the idea of extraterrestrial life. Some of his predecessors faced persecution for daring to suggest such a possibility. However, Wells's imaginative storytelling was truly groundbreaking. His radio play, based on his work, caused widespread panic in the USA when listeners mistook it for a real alert. Even two-time British Prime Minister Sir Winston Churchill pondered the question in a 1939 article titled, "Are We Alone in the Universe?" He expressed skepticism that humanity was the sole intelligent life in the vast cosmos. Film and television have long capitalized on the idea of extraterrestrial beings, spawning a billion-dollar entertainment industry. But what if instead of passively waiting for aliens to come to us, we actively sought out life beyond our world? Science is rapidly catching up with these speculative visions, and our search for extraterrestrial life is becoming increasingly sophisticated, exploring the origins and evolution of life. Our planet is teeming with life, from the scalding depths of volcanic vents to the icy peaks of mountains and the frigid expanses of polar regions. These life forms, based on complex DNA and carbon, have adapted to thrive in diverse environments. Interestingly, our exploration of the solar system has shown that space is not barren either. Asteroids, comets, and meteorites carry organic compounds, challenging the assumption that these compounds are rare beyond Earth. However, these carbon compounds are not merely simple molecules, they are complex and rich in carbon, nitrogen, and hydrogen. The distribution of these fundamental building blocks throughout the solar system suggests the potential for life to emerge elsewhere. The question of where life can exist rapidly becomes complex. While Earth's DNA complexity offers insight, we wonder about environments capable of fostering similar complexity. Can life arise in the harsh conditions of our solar system?
With only one example of life on Earth, we lack concrete evidence to answer definitively. Solar systems possess all the necessary ingredients for life, but the exact process of life's emergence remains elusive.
The environment that supports life now might not be its origin. Life thrives in diverse habitats, from rainstorms to Antarctic ice caps, enduring harsh conditions for extended periods. However, understanding how life begins requires detaching from current environments and focusing on the building blocks of life. Life, as we understand it, is a marvel of complexity capable of self-replication and diversity, yet the transition from basic organic chemicals to functioning organisms remains a mystery. Essence of life. The definition of life remains a subject of ongoing debate among biologists and scientists. In essence, life comprises self-contained systems that harness external energy to generate biomass, leading to growth and replication. One prevailing hypothesis suggests that the precursor molecules necessary for life, such as amino acids and nucleic acids, were readily available on Earth before life emerged. It's speculated that lightning may have played a role in sparking reactions among fundamental chemicals, like carbon, nitrogen, and oxygen, forming these vital building blocks. However, an alternative hypothesis proposes that these compounds were not abundant before life's emergence. Instead, life itself may have facilitated the creation of these molecules by harnessing pre-existing energy sources, particularly hydrogen, to convert carbon dioxide into organic carbon. This process likely evolved gradually, leading to the formation of amino acids and proteins, along with increasingly complex chemical reactions. The question of whether life beyond Earth relies on the same building blocks remains contentious. Nonetheless, organic carbon is believed to be crucial due to its flexibility and stability, enabling the polymerization necessary for life's complex chemical reactions. Meteorites, remnants from the early solar system, offer promising avenues for astrobiological exploration. They contain essential molecules, such as amino acids and nucleic bases, which could have seeded Earth with the building blocks necessary for life's evolution. Moreover, meteorites provide a conducive environment for microorganisms, offering abundant resources like phosphorus and organic matter. The study of meteorites unveils insights into the violent history of planets, with debris often ejected into space during collisions and volcanic eruptions. By analyzing meteorites, scientists can decipher potential biomarkers left behind by life and gain a deeper understanding of life's origins and evolution in the cosmos. The mysteries of ancient fossils and life's emergence. The tale of a meteorite's journey from Mars to Earth, spanning millions of years, unveils tantalizing hints about extraterrestrial life. Among the most debated meteorites is the Allen Hills meteorite, believed to harbor nanobacteria from Mars. While some studies suggested the presence of microfossils resembling life forms, the evidence remains ambiguous, challenging scientists to discern between geological formations and true biological traces. Astrobiologists, intrigued by the quest for early life, focus on microfossils preserved in rocks. These fossils, often single-celled microorganisms or microbial communities, provide vital clues about ancient ecosystems. Conditions favoring fossil preservation typically involve mineral replacement or chemical alterations induced by microorganisms, leading to the formation of distinct mineral structures. Recent breakthroughs, such as the discovery of stromatolites in Greenland dating back 3.7 billion years, shed light on the rapid emergence of life on Earth. These ancient rocks, preserved amidst a tumultuous period known as the Late Heavy Bombardment, suggest that life may have arisen surprisingly early in Earth's history. Such findings challenge previous assumptions about the time required for life to evolve complexity, hinting at the possibility of life emerging within relatively short geological timeframes. However, the implications of these discoveries extend beyond Earth, inspiring renewed interest in the search for life elsewhere in the solar system and beyond. Hot springs as crucibles for complexity. Recent discoveries are reshaping our understanding of where life may have originated on Earth. While the prevailing theory suggests life began in the deep oceans near hydrothermal vents, new insights challenge this notion. The process of creating complex organic molecules, essential for life's emergence, requires not just water, but also drying conditions, something lacking in the ocean depths. Instead, scientists are turning their attention to hot springs, which offer ideal conditions for the formation of complex organic molecules. Unlike the extreme conditions of deep-sea vents, hot springs provide a more hospitable environment with fluctuating temperatures and chemical compositions conducive to chemical reactions. Each hot spring is unique, with varying pH levels, nutrients, and chemicals, contributing to the diverse array of organic compounds. This paradigm shift has significant implications not only for understanding life's origins on Earth, but also for exploring the potential for life elsewhere, such as Mars. Unlike Earth, Mars lacks deep oceans, but boasts a history of volcanic activity and hot springs, making it a promising target for investigating the origins of life. Is there any life on Mars? As scientists delve deeper into the mysteries of life's origins, Mars emerges as a prime candidate for exploration. Positioned closest to Earth in both time and space, Mars offers a tantalizing opportunity to uncover evidence of non-terrestrial life. Recent discoveries on Earth, from Greenland to Western Australia, have highlighted a crucial time window in Mars's history. Approximately 3.8 to 3.5 billion years ago, Mars boasted warm, wet conditions, ideal for the emergence of life. Volcanic activity, flowing water, and chemical complexity were abundant, mirroring the conditions necessary for life on Earth. The upcoming Mars rover mission, Rover 2020, represents a pivotal moment in our quest for ancient signs of life. Landing site selection is a meticulous process, with scientists and technicians carefully evaluating potential locations. Among the top candidates are sites believed to contain hot spring deposits, silica formations formed by extruding hot water. Excitement abounds as these deposits bear striking resemblances to formations found on Earth, particularly in the Pilbara region, where ancient life thrived in active hot springs billions of years ago. Textures resembling finger-like structures, indicative of microbial activity, have been observed in opaline silica deposits on Mars, sparking intrigue and anticipation among researchers. The parallels between Martian deposits and Earth's hot spring environments are striking. Known hot spring deposits on Mars beckon exploration, offering the possibility of uncovering evidence of ancient microbial life. As scientists eagerly await the Mars 2020 mission, hopes are high for groundbreaking discoveries that could reshape our understanding of life's potential beyond Earth. Signs of life, methane, and planetary protection. In the quest for extraterrestrial life, scientists are closely monitoring the detection of methane gas in the Martian atmosphere, a potential indicator of life processes. While geological processes can produce organic molecules, including methane, through reactions such as serpentinization, the presence of methane raises tantalizing possibilities of biological activity. The hope of discovering fossilized microorganisms on Mars is a driving force for scientific inquiry, offering profound insights into the origins of life. However, the journey towards such a discovery is uncertain and may require extensive exploration efforts. Yet, the search for alien life faces another challenge: contamination. Earthly bacteria hitching a ride on spacecraft could inadvertently contaminate Mars, compromising the integrity of scientific investigations. Planetary protection officers meticulously oversee mission protocols to minimize the risk of contamination, ensuring the preservation of Martian environments for future exploration. The Mars 2020 mission exemplifies this cautious approach, focusing on studying ancient rocks rather than actively seeking existing life forms. Ice moons, potential havens for extraterrestrial life. The icy moons of Jupiter and Saturn stand as the next frontier in our search for potential habitats beyond Earth. Dr. Helen Mayed-Casley has dedicated her research to studying the planetary conditions of these distant worlds in laboratory settings. Among these moons, Europa garners significant attention due to its believed thick ice crust concealing a global ocean beneath. This subsurface ocean, nestled against a rocky mantle, presents a unique environment where water interacts with minerals and nutrients. Shielded from Jupiter's intense radiation, Europa's ocean offers a promising haven for life to thrive. Similarly, other icy moons, such as Enceladus, also boast subsurface oceans, sparking fascination within the scientific community. These environments evoke questions about the origins of life as they mirror Earth's own chemical hot springs where primitive organisms flourish. The presence of liquid water on these remote moons opens new avenues for exploration and underscores the potential for discovering extraterrestrial life forms. As scientists delve deeper into the mysteries of these icy worlds, the quest for understanding life's origins beyond Earth takes on renewed significance. The mysteries of Europa and Enceladus. The question of life's complexity and its origins takes center stage when contemplating the icy moons of Jupiter and Saturn. Dr. Helen Mayard Casley offers insights into the geological dynamics of these distant worlds, shedding light on their potential as habitats for life. Europa and Enceladus, with their subsurface oceans and potential for geological activity, present intriguing targets for exploration. However, the fundamental question arises: can these environments support the emergence of complex life forms? While the deep oceans of Europa and Enceladus may lack the crucial cycling of wetting and drying necessary for life's complexity, there remains speculation about the role of meteor impacts in delivering organic chemistry to these moons. Cratering patterns on Europa suggest potential pathways for materials to penetrate its icy crust, influencing the subsurface environment. Enceladus, despite its small size, surprises researchers with its immense geysers and hidden ocean beneath the South Pole. The source of its heat remains a subject of debate, whether from tidal forces or radiogenic heating. Nevertheless, the presence of an ocean hints at the ingredients for life, though uncertainties persist regarding its extent and interactions with the rocky crust. As scientists navigate the complexities of these icy worlds, the quest for understanding life's origins beyond Earth propels us forward, offering tantalizing prospects for discovery amidst the frozen expanses of our solar system.